the PIQs. Okay, so if you go to Moodle and search under today, you will see multiple PIQs. If you choose the first one, 8.2, we can start with that. Okay, so we'll go through them one at a time. So we start with this question. There. Each plane, we have 3 planes flying at the same level, at the same speed, at the same height. And they release tanks, each in a different position. If we ignore air resistance, which tank has the largest speed? Now remember, the only thing here acting on them is gravity. There is no engine in the tank or anything. So take out of time, think about it. So this is basically a revision on conservation of energy. أول واحد 8.2 سالم. Okay. Of 83 people joined, about 10 people, 15 people still haven't joined. And we have 28 of them who still haven't responded. So I'll give you about 30 more seconds. بعدنا نسخن بداية. Take some extra time. Okay. Let's see how it went. So, the vast majority of people have chosen each tank hits the ground the same speed. A few people chose B, a couple chose A and C, but most people chose the last option. And the last option is indeed the correct option. So this is a revision of what we have been doing on conservation of energy. Now, at first glance, this question looks a bit weird. Okay, he is asking us about speed, but he has not given us distance, he has not given us height, he has not given us initial velocity, he has not given us, I haven't really given you much information to go with. So our normal equations of V equals U plus AT, of S equals UT plus half AT squared, of V squared equals U squared plus 2AS, we cannot use any of them. What we can use, however, is that since they're all at the same height, we can say, okay, in terms of energy, the gravitational potential energy here is equal to mgh for all of them, since it's exactly the same tank. At the ground level, GPE for all of them would be equal to 0, and so kinetic energy for all of them would be equal to half mv squared, which is equal to the initial mgh. So they all hit the ground with the exact same speed. Any questions on this?
Doctor,
أيوة.
the angle not affect.
No, it does not. Since the question says it is released, okay, it is basically just left there. Now, at what angle do you leave it? Imagine holding a pen and then just opening your hand and starting to drop. So the angle at which you, okay, I want to be as accurate as possible when answering you. The angle at which it is released, if we are ignoring air resistance, okay, does not make a difference as long as the thing does not start to rotate. So if this thing releases it at this angle and then it starts rotating, what would happen? Can you imagine? Anyone?
Repeat, doctor.
If إذا الفيول تانك هذا بدأ يسوي روتيشن، يدور في الهواء وهو يطيح، what would happen?
If we have air resistance, it will slow down.
Okay, if we have air resistance, it will slow down, but we're still ignoring air resistance. But the thing is now rotating. Does it affect the conversion of gravitational potential energy to kinetic energy?
No.
No, okay. Does anyone disagree with the no? So question, when something rotates, does it need energy or not for rotation?
Need?
It needs energy, right? Have you ever played with what is it called? نسيت اسمه. كنا نلعب فيه دائما واحنا صغار. لولب. تلف حوالينه حبل وبعدين تسحبه و just keeps يدور يدور يدور. ايش تسموه؟
بي
بليد, yes. That's one option. انا اتكلم بعد عن موديل اقدم بس بي بليد is an excellent option. Yo-yo is also another excellent option. Okay. Everyone here knows B-blade? Yeah. So
Yes.
in B-blade, what you're doing is it starts rotating, 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 and then eventually it slows down, right? Why does it slow down? Why does it stop? Because it ran out of energy. Everything needs energy. So what happens is, if option A, B, and C, there is no rotation, the angle does not make a difference. If, however, this thing starts rotating needs energy, then what would happen is the gravitational potential energy is going to be distributed in two paths. راح يتوزع. Part of it will go to linear kinetic to translational kinetic energy, and part of it will go to keep it rotating. So you will end up with a slower velocity for any rotating objects. Okay? We will study more about rotation and rotation dynamics in chapter 10, I believe. Okay. Any other questions on this? Okay. This is a very interesting question. And what we will do is, I will put it here. And this is quite an interesting question, and it's tricky too. Okay. You have two people going down a slide. Okay. And the question is two parts. Which one is traveling faster at the bottom, and which one reaches the bottom first? And this is quite tricky. So what we'll do is we'll do it in the breakout rooms as groups. Okay. So let me set up the breakout rooms. We have okay. Okay. So let's give it a go. I'll give you about 4 minutes maybe for this question. Let's see what we can come up with. Okay? Ready? Let's go.
Can't hear you, doctor. Do you open the mic?
Sorry, I've been talking to myself. That's always fun. Okay, so I said most people got at least one of the two questions right. We'll do it together to discuss the thought process going behind it. Now, just like the airplane, both Paul and Kathleen start at the same height, at the same point. So they both start with an energy of mgh. They both end up on the floor at the same point, at the same height. And mgh down here is equal to 0. Where did this energy go? This energy went to kinetic energy because we are ignoring friction. So we end up with half mv squared, which is equal to mgh. So assuming they have the same mass, they will end up with the same velocity. Okay. Assuming they start at the same position, they end up at the same position, they have the same mass, they will end up with the same velocity. So they both have same velocity. But. Now the other question is, which rider reaches the bottom first?
Doctor,
Yeah.
they don't have to be the same mass, right? Because the m will cancel.
Yes, that is also correct. They don't have to be the same mass because the m's will cancel out. You're absolutely correct. For which one has the fastest velocity, the m's will cancel out. So you don't even have to be the same mass. They will still have the same velocity. But which one reaches the bottom first? Now, some people chose Paul. Some people chose Kathleen. And some people chose both will reach at the same time. So first thing first, can someone who chose Paul tell me why Paul? No? Okay, can someone who chose Kathleen
Yeah,
tell
me,
me why Kathleen?
me, Doctor, I choose Paul, and I was thinking that he's traveling with the longer distance with
Okay.
an acceleration 9.8. So if his velocity is increasing every second 9.8, he have more time, more
Okay,
distance. I mean.
but they are going through the same vertical height, h. They both
Yeah,
start at the same height, h.
but Kathleen like stops in this point. Kathleen won't have the same acceleration 9.8
Why not?
because something is preventing like the surface.
No, but Kathleen is still going down. Okay. What about someone who chose Kathleen? Can you tell me why Kathleen reaches the bottom first?
Because she in the lower elevation.
Okay, and how does this affect her?
Doctor, sorry, I was talking about the previous question, not this one. I was
Okay.
talking about A.
Okay. Now for B. Okay, here is something. They both start with mgh. They both end up with half mv squared. And we agree that if at the beginning they had 100 joules of mgh and 0 joules of Ke, at the end they will have 0 joules of mgh and 100 joules of Ke. Right?
Yes.
Okay. But then the question is, how fast is the mgh being converted to Ke?
Mr.
Yeah.
Oh, so if someone just drops straight down from a building and someone slides across, it's the same thing.
It's what? Sorry?
If we have like a 100-meter building and we slide down all the way, we'll have the same MGH at the start, but MB at the end. Like if you drop someone else from the same height just straight down, it's different.
Your velocity at the end is the same, whether you drop down or not. So if Paul instead decides to jump from here and go straight down all the way to here, his half mv squared here would still only be equal to mgh, because that's all the energy available to him.
But why then, when you jump straight down from like a 3-story building, you're going to die? And if you slide down, you're not.
Because so you're asking if I jump straight down from a building, I die, and if I slide down from a 100-meter building, I don't die. Why does that happen, right?
Yeah.
So we will answer this in detail in the next chapter, actually, chapter 9. But let me ask you something. Which one experiences the more force when they hit the ground? The guy who jumped straight down or the guy who's, on a slide?
Straight down.
Straight down. Straight down immediately goes, from some velocity to 0. Okay. And the force is huge, so they end up dying. Now, mind you, if you are on a slide, have you ever been on one of these really big slides في على أيامي أنا كان في حديقة الوادي الكبير وكان في حديقة النسيم والريام الزحلوقة الواجد طويلة هذيك اللي يحتاج لك 10 دقائق تصعد الدرج فيها توصل فوق. Have you ever been on one of these?
Yes.
Okay. And what I'm going to say has been very, very graphic, will be very, very graphic. So please excuse me for that in advance. Okay. In that thing, okay, in that slide, it's a long slide, and you slide down the whole thing. And when you finally reach the bottom, what happened to your bottom side?
Yeah, it will burn because.
It burns, right?
Yeah.
Because you have a lot of energy there and you're losing it as friction. So your bottom side actually ends up burning, right? Now that slide is usually, 5 meters, 6 meters. Now, if you go up 100-meter high slide, okay, the amount of kinetic energy you are going to have at the end, okay, you might not die because your energy transfer will not go from kinetic energy to internal energy. So basically what happens when you fall down straight, you have 10,000 joules of kinetic energy and you immediately stop. But then when you stop, your kinetic energy became zero. Where did it go? It goes inside your body as internal energy, but it's such a huge thing. It's as if you are releasing a bomb inside your body. Yeah, حرفيا يفتت أعضائك من داخل. لذلك إذا if you watch movies where someone jumps and dies or something like this, or dies due to an accident, what do they say? Death due to blunt force trauma. Yeah, it's that huge transfer of a huge amount of energy in one go. Basically, your body cannot withstand it, so it ends up breaking up. الكبد عندك بدل ما يكون قطعة واحدة, so much energy, it shatters into 100 pieces and so on and so forth. And you end up dying from hemorrhaging or from bleeding or something like this. Okay? But if you slide down those same 100 meters, you might not die because that energy does not instantly transfer to the inside of you. But what happens is that energy will cause a lot of friction. Okay? And if you thought burning your bottom on that 5-meter slide was bad, imagine a 100-meter slide. Imagine the amount of energy that's going to go into your rear side while friction slows you down to a stop. I imagine that would be like 2nd or 3rd degree burns. That would require hospitalization at the very, very least. Okay. Now we're having some very interesting graphic conversations. Okay. But back to the point. Okay, so what happens here is كاثلين تحول طاقتها 100 جول إلى kinetic energy أسرع لأنها جالسة تنزل أسرع. Okay, so if I look at this random point, إنزين حجي بول حي الله مغطي هذا المسافة vertically. So only this amount of mg delta h becomes kinetic energy. بينما حجية كاثلين is already halfway across in terms of height. Right? So the kinetic energy here, say for example, if mgh here is equal to 90 and kinetic energy here is equal to 10, here, halfway through, you are more at 50-50. So Kathleen converts her potential energy to kinetic energy much quicker, and that is why she reaches first. They both reach the same speed eventually, but it's like comparing a drag race between a Porsche and a Corolla. البورشه بتوصل 120, الكورولا بتوصل 120, بس واحدة فيهم بتوصل خلال 3 ثواني والثانية بتاخذ 20 ثانية عشان توصل. Final velocity, same, 120. But which one reaches first? The Porsche. Is that a bit clear? Yeah? Okay.
Doctor,
Mm-hmm.
they mentioned that the length of the two slides are the same. So if one was, for example, shorter, it has, what's the difference?
Shorter as in this
The
length
length.
shorter, or shorter as in lower vertically?
No, not vertically, the same height.
Same height, longer length makes no difference in terms of final velocity. It will still be the same.
Yes, but the time.
The time will depend on the angle. So, say for example, they both start here. Okay. Say for example, they both start here. Now, your question is, say هذه منهجية Kathleen, and actually, let's do it the other way around. My Kathleen is very steep but very, very long. Okay. And my Paul will be less steep but less long. Something like this.
Okay.
Is this what you mean?
Yeah. It's
Okay.
like the example, I don't know who mentioned sliding from the building and falling down from the building. They start
So
from
the
the same
final
height.
velocity would still be the same.
Yeah, they both start with the same height, but they have different lengths. They
Yeah, but the amount of energy available is still only mgh.
yes.
So your kinetic energy, whether here or here, will still be equal to only mgh. ما عندش أكثر.
Yes.
Yeah. على قولة إخواننا المصريين الضرب في الميت حرام. You only have mgh. You cannot give more than mgh. It doesn't matter what you do. Short, long. Yes, in terms of time, okay, things might be different. It could be, if one of them was longer than the other, that the result would be different. Maybe Paul reaches first, but it really depends on the path. But as long as the paths are the same length, then Kathleen is converting her energy first, so she will reach first. Okay. All right. So this is this. We now move on to this. So we spoke about forces, we did section 8.4 and 8.5 last week as well. So let's do a sample problem and we'll do it together. I have way too many tabs open. Okay. Not this. This. And we go to 8.06. Okay. Another water park slide. And this is, for example, how some real applications in the world do. So we have a water slide in which a glider is shot by a spring. So you have a spring at the beginning here, look. And it shoots you in a ride, okay? You glide down, first horizontally and then down, okay? Now the actual slide is frictionless. There's a lot of water on it, okay? This is like Wild Wadi. But when you reach to the actual end, to the ground level, okay, it stops due to friction. Mass of the glider and the rider is about 200 kilograms. Compression of the spring initially is about 5 meters with a constant of 3.2 times 10 to the power 3 newtons per meter. And our height is 35 meters. Coefficient of kinetic friction along the ground level is 0.8. Now, what we want to know is at the ground level, how much will it slide? Okay. Now, what's the easiest way to do this question? We want to know here, down here, how much will it slide? Okay. What is the total amount of energy we have here?
MGH.
At the top, we have MGH, but we have also something else. We have a spring. So we have MGH and the potential energy of the spring. MGH and half kx squared, right? Kinetic energy at the top is 0. Now here, you don't have any friction. You keep going until you reach here. Now, when you reach here at the end of this slide, what is your energy components? What are your energy components?
K.
Okay, you have kinetic energy.
And the spring.
Spring.
Does the spring come down with you, or does it stay up there?
No. Friction.
So the spring gives you the energy, and the energy is now with you, صح?
Yes.
Yes.
Okay, so then the only energy you have down here is kinetic energy, nothing else. And حرامي درجة أولى شحفت spring energy والgravitational potential energy شرت فيه حولته كله لkinetic energy. صحيح؟ Okay. What about here at the end? بعد ما الفريكشن يعمل عمايله. What type of energy we have at the very end? Do we have gravitational energy?
No.
Do we have elastic potential energy?
No.
Do we have kinetic energy
Yes.
after the friction acts?
No.
After it stops?
No.
No.
So where did where did the energies go? كان عندنا واجد في البداية، كان عندنا MGH وكان عندنا half kx squared. وين راحوا؟
Lost.
Lost to what? To friction.
Heat.
So they all go to E thermal due to friction. Now we can actually start doing the calculation. Friction is mu k mg, and the work done by it is that times the distance, which is the length L, which is what we want to find. So my friction is equal to my initial MGH plus my initial half kx squared. أعيد الترتيب to get L as the subject, and we put in the numbers. Okay. Now, if I do the numbers, half kx squared is how much? Half times 3.2 times 10 to the power 3 times 5 meters squared. So this is about 40,000 joules. MGH is 35 times 200 kilograms. So this is 7,000 joules. So the total of this is 47,000 joules. Now, if I do 47,000, which is this, divided by this, 0.8 times 200 times 9.8, I end up with about I made a mistake somehow. Because I'm not getting 69.3 meters. I'm getting 4.46 meters. Did anyone else do this calculation? Is anyone doing it now and trying to help me? Am I talking to myself? Did I disconnect?
No.
No, you didn't.
So where did I make the mistake? This is not 7,000. This is where I made a mistake. ما حد جالس يساعدني ويشيك معاي. This is 68,600, which means my total is 108,600. If I do this calculation again with the right energy, I do end up with 69.3 meters. Any questions about the sample problem? No? Okay. Let's see if we have actually understood. ولا جالسين تمشوني على قدام. Okay. Let's take a look at the PIQs for sections 8.4 to 8.5. Actually, let's just do it on Google. Okay. A car is moving along a horizontal road at 20 meters per second. The driver then hits and locks the brakes. The coefficient of kinetic friction between the tires and the road is 0.8. How far will the car slide? Use conservation of energy. Find it out. Okay. And type it in the chat section. Abdul Wadud, it means u equals 0, not k equals 0. K it can have a velocity when it reaches the bottom. So once you're done with the calculation, just type it up in the type which answer you think is right, A, B, C, D, or E, in the هذا في الchat.
So, doctor, we don't have IQ in the model.
Sorry, say that again.
We don't have this question in the model.
No, not on Moodle. Just type it in the chat. Okay. Let's see. Pretty much everyone chose 26, which is option C. So let's see if it is option C. So it's moving at 20 meters per second, meaning kinetic energy is equal to half mv squared. Why is it not writing? Half mv squared. It hits the brakes and there is friction. Friction is equal to mu k Fn, which is mu k mg. Since it stops completely, okay, this means that we have half mv squared becomes mu k mg. The m's cancel out. Oh, sorry, mu k mg d. I forgot about this bit. Yeah, right, mg. So half mv squared mu k mg d. So d will equal to v squared over 2 mu kg, which is equal to 25.5, which is approximately 26 meters. Well done. Now, a common thing, which I'm very happy to see you guys did not do, a common problem with students is that they start this question, they write KE equals half mv squared. السؤال ما في وزن. That's it. This problem cannot be solved without knowing the mass. I'm very happy you did not do that. You actually wrote down the entire formula and saw that the m's can be cancelled. Okay, it's always important to write the formula to see where you can simplify, because if you try to do this with numbers alone, then KE half mv squared ma عندي m, oops, I'm stuck. Okay, now there's one tiny important bit. Okay, that we said external force is what takes out energy or puts in energy, right? They do work. Now that is correct. If we want to do work, we have to have an external force. But external force do not have to do work. They can act on a system without doing work. Okay? This is like asking, هل الأرنب أبيض؟ نعم. هل الأبيض أرنب؟ No, not necessarily. I can have many things that are أبيض, not necessarily rabbits, right? So in this this is called في علم المنطق باللغة العربية يسمونه العموم والخصوص من وجه. So it's a one-way road. Okay. So every work needs to be from an external force, but not every external force means that there is work done. عندي بعوضة مقبتني من الصبح ورجاية رايحة وما قالت امسكها. شو الحالة؟ Let's take an example. We have a skater on ice. Now the skater pushes herself away from the wall. Okay, so the external force is what? Is the push from the railing, right? This is the external force. So what is she doing when she is actually, pushing? When she is pushing, way too many tabs open. Okay, nobody's in the chat. What she is doing is, okay, that she turns, because she's pushing using her body, she is converting her internal chemical energy in her body, in her muscles, to kinetic energy. Now, her kinetic energy is caused by the force from the wall. But it's not the force from the wall that is providing her the energy. It is her chemical energy from inside. Is the idea here clear? That there can be forces acting without doing actual work?
No, doctor, can you repeat, please?
Okay, so this person تدفر نفسها تدفر على الجدار وترجع ورا. Okay, now if I ask you, what is the force that causes her to move? إيش بيكون جوابك؟
Her energy.
مش energy, what force?
Push.
Push of the wall on her body, صح؟ Newton's third law. هي دفرت الجدار دفرها. تضربني بضربك، صح؟ So the force she is moving is from the wall on her. لكن الانرجي من وين جاء؟ هل الطاقة جاءت من الجدار؟ لا، الطاقة جاءت من داخل جسمها. بالتالي the force of movement is from the wall, but the source of energy for her movement is not from the force itself. It's not from the wall. It's from her inside. Last thing last, expanding the definition of power. In general, power is the rate at which energy is transferred by a force from one type to another. We have done this before. And we have said that if some energy is transferred in some time t, then the power is delta E over delta t. And the instantaneous power is dE over dt. Right? We have done this before. This is not new. "15 minutes left." So we finished up until 8.5. Now we go back to 8.3. This is a bit mathematical, so I left it to the end. Okay. Reading a potential energy curve. So far we have been saying عندنا potential energy, عندنا potential energy. لكن طيب هذا potential energy, how do we use it? Okay, one option is mgh or half kx squared equals kinetic energy, but are there other uses to it? Turns out, yes, a lot. In your book, we said that there is an equation, delta u equals minus the integral of fx dx, which is nothing actually new. This is just simply f dot t integrated over a path. عملناها قبل، صح؟ But now if I want to do the reverse, if I have u وأريد منه f، إذا عندي البوتنشال وأريد الفورس، كيف أسوي؟ The reverse of integration is taking a derivative. So I do minus du by dx. So if I have a curve that is the potential versus the position, I take the slope minus the slope is my force. Now there's something very important here. This is only true for conservative forces. Okay, non-conservative forces هذا ما ينفع. You need to do other stuff. Okay, let's take it in one dimension. My potential energy for a spring is half kx squared. What will my force be?
Integration of what, u?
If I have f and I need u, I do integration. If I have u and I have f, what do I do?
مشتقة اليو.
Yep. So what will it give me? What will my result be?
kx, but minus.
Yep. Minus kx. Which is what? Hooke's law. For a spring f equals minus kx. ما نحن بدأنا الهلمة هذه كلها مع السبرينج و f minus kx. صح؟ Okay. For gravitational potential energy, it is mgh or mgx. What's the force? Force is equal to F minus mg. Gravitational force, لا? F equals mg. الوزن. Weight. Nothing really complicated. Now, if we write the mechanical energy of a system, okay, only the mechanical. خلينا من الفورس والاشياء الثانيه الاكسترنال والثيرمال وهذا، فقط mechanical for the time being. Well, sum of the potential and kinetic energy is my total mechanical energy، صح؟ طيب. This gives me an important limitation. ايش قلنا قبل شويه لما كنا نتكلم عن مثال الزحلوقه؟ قلنا it doesn't matter how long you go, انت ما عندك اكثر من 100 جول. You cannot give any more. That is your limit, right? Well, here's another way to explain it. My kinetic energy is my total mechanical energy minus my potential energy. Yeah. So it gives me a limitation. Yeah, of how much kinetic energy I have. Is this clear or is it confusing? Okay. Let's talk about something called turning points. So اليوم نحن راح نتكلم عن شيئين ثلاثة شوية كأنهم ما مترابطين, but they will start coming together soon. Look at this pendulum. When it reaches at the very end, there's something happening, right? If you remember in the previous... Sorry? What did you say? What did you say? Sorry.
I'm just was answering you that when it comes with a turning point, k equals 0.
That is correct. That is absolutely correct. No, open. Yes, thank you. At these points, like we saw in that simulation last week, we call them equilibrium points. My kinetic energy at these points are equal to 0. My velocity there are equal to 0, but my force is not equal to 0, right? This is why it starts coming back down again, because there's a force bringing it back down. Let's take a look at not for that, just for general system, a plot of potential energy versus position. Just some wiggly line. We know that force is minus du by dx. So if I look at the slope of this and plot it, I end up with the blue line. So right about here, my potential is maximum, the slope is 0, so my force is 0. About here, I have a very strong slope, so I have a very positive force. Here, my slope is again 0, so my force is 0, and so on, and so forth. Yeah? Okay. We know that the sum of the kinetic energy and the potential energy is equal to the mechanical energy. Let's say, for example, my total mechanical energy I have is 5 joules. Now, when I want to find out how much motion am I allowed to make, لازم أشوف كم الطاقة اللي باقية عندي، صح؟ إذا أنا عندي 5 جول توتال وجاي في منطقة معينة البوتنشال فيها أساسا 4. كم اللي باقي عندي عشان أحوله كينيتيك؟ جول واحد بس. half mv squared equals 1 جول وأشوف ال v كم يطلع لي. هذا حدي. I cannot go faster than that. Right? Correct?
Yes.
Okay. Here I have a much lower potential energy, so I have a higher kinetic energy. And so on and so forth. Yeah. Now we're going to have a problem. ايش يسوي هنا؟ My potential energy هنا أكثر عن my total energy. My total potential is more than my total energy here. My total energy is 5 joules. My potential energy here is 6 joules. So what is my available kinetic energy? Negative. So -1, right? So if I do my kinetic energy is equal to -1 joule is equal to half mv squared, that will mean my v squared is equal to -2 على m, which means that my velocity is the square root of a negative number, which is what? Have you studied this? The square root of a negative number is what?
Undefined.
Undefined is one answer, yes. Have you studied imaginary numbers yet? Nobody here studied imaginary numbers ever? Ooh, fun. So you will learn soon enough in some course, okay, that the square root of -1 is equal to I. Otherwise known as I squared equals -1. Okay. Now depends, if you are taught by an engineer, they will not use I, they will use J. And here they will say J squared. But it's the same thing. Okay. Now this is very, very weird. Okay. So if I tell you Square root of minus 4, you'll be okay. This is square root of minus 1, square root of 4, which means 2i. And this is an imaginary number. Okay, this is just there in mathematics. It's not there in real life. Okay, so as the name implies, it's imaginary, okay, or otherwise known as complex number. ما علينا من هذا in this course, okay. But here's my problem. My kinetic energy cannot be negative because I cannot have a negative velocity. Yeah, sorry, I cannot have a negative kinetic energy. Okay, v squared cannot be negative unless you're in the complex plane, and then that's just too complicated for this course. So this is simply not possible as far as our course is concerned. So what do I do when I'm analyzing this part of the plot? I say that I cannot move in that direction. It's simply not possible. كأنك تقول لي أخوك الصغير اللي طوله اللي عمره 2 وطوله 30-40 سنتي جاي قدام جدار البيت اللي ارتفاعه 4 متر ويبغى يطلع، يصير؟ ما يصير. It's not possible. Okay. Now, turning points are the points where we have a kinetic energy equals 0, but the force is not equal to 0. Okay. So you have maximum force, or you have some force, much of maximum, but your kinetic energy is equal to 0. Okay. I will reduce my total mechanical energy. بدل 5 جول أسوي 4 جول. Good. At these 2 points, my force is not equal to 0, but my kinetic energy is equal to 0. At this point, my force is not 0, but my kinetic energy is 0. At this point, my kinetic energy is 0, but there is no slope. So my force is also equal to 0. And this is what we call equilibrium points. Okay. Now we have 2 types of equilibrium. I will skip over this. Okay. There we go. We have 2 types of equilibrium. Skip. There. I need this, an empty page. Sometimes you have something like this وتحط لك اللولو، حبة اللولو هذه هنا فوق، وتحطها بحذر وبشوية شوية. And although this thing is curved, حبة اللولو ما تتحرك. صحيح؟ It's perfectly balanced. Or you can do this to a pencil مثلا. صح؟ Sometimes تحط حبة اللولو في ملة بهالطريقة. What's the difference between these 2? What happens to the marble if I try to push it in case number 1?
In 1K equal to 0, and 2K is the largest.
In both cases, K is equal to 0 because they're not moving at the moment. أنا جيت حطيت له حبة لولو على ملة، مرة ملة مقلوبة ومرة ملة سيدة. في كل الحالتين it's not moving. But there is a key difference. في الأول إذا مسيتي اللولو ولو بنسمة هواء, what's going to happen? It will gain kinetic energy very, very quickly and it will fall. صح? But in the second case, what will happen is بيصعد شوية فوق, يوصل هنا, ويرجع مكانه ولا كأنه شيء صار. And this is the difference between what we call. So this is what we call a neutral equilibrium. نحن هنا. And this is what we call an unstable equilibrium. If you are here in the potential plot, أدنى حركة, you will fall down very, very quickly. But if you are here, you need a lot of energy to go out. Most times what will happen is بتوصل هنا بتخلص الانرجي بترجع وين ما كنت. You're protected. Yes. Okay, that's pretty much it for today. Yeah, that's pretty much it for today and for chapter 8. Next week, next week, يوم الأربعاء, inshallah, we start with chapter 9. Okay. Fatima, in the quiz, up until the end of last week, what we did last week. So conservation of energy will be included, but this whole potential graph thingy is not included. Okay, so pretty much to be safe, you can say up until the end of 8.2.
Okay, thank you, Doctor.
Yeah. So if I look at the work plan, it says chapter 7 and chapter 8. So all of chapter 7 and 8.1, 8.2. That's it. Okay. Stop recording.